You're looking at something red right now. Maybe a shirt, maybe part of a screen, maybe nothing. Doesn't matter. You know what red is. You've known since you were 3 years old. Red is red. Except, here's the thing. Red doesn't exist. Not the way you think it does. Not out there in the world. And once you understand why, you can't see anything the same way again. Let me show you what I mean. Take that red thing you're looking at. What makes it red? You'll say the light coming off it. Fine. What makes the light red? Now you're stuck, because light doesn't have a color. Light has a wavelength. About 650 nanometers for what you call red. That's a distance, the space between peaks of an electromagnetic wave. Distances don't have colors. They have lengths. So where's the red? Not in the light. The light is just an electromagnetic wave oscillating at a particular frequency about 460 terahertz. No color there either. Just a number. A vibration in the electromagnetic field propagating through space at 299,792,458 meters per second. The same kind of thing as a radio wave, an X-ray, or the signal that makes your phone work. Those don't have colors. Neither does this. Still, you see red. Vividly. Undeniably. So something is creating it. Let's follow the path. Light at 650 nanometers hits your eye, passes through the cornea, the lens, lands on the retina at the back. There, it encounters molecules called opsons, sitting in cells called cones. You have 3 types of cones. One type responds most strongly to light around 420 nanometers short wavelength. Another peaks around 530 nanometers, medium wavelength. The third peaks around 560 nanometers, long wavelength. Here's what happens. That 650 nanometer light hits the long wavelength cone. The opsin molecule absorbs a photon. The absorption causes the molecule to change shape. That shape change triggers a cascade of chemical reactions. Sodium channels close. The cell hyperpolarizes. The voltage change reduces the release of glutamate neurotransmitter. Neurons downstream detect this reduction. They fire in a particular pattern electrical signals, chemical concentrations, voltage differences. Still no color. These signals travel through the optic nerve to your brain. First stop, the lateral geniculate nucleus in the thalamus. Then to the primary visual cortex, V1, at the back of your brain. From there to V2, V4, other processing areas. At every stage, neurons firing, ions flowing, neurotransmitters releasing. Electrochemical events, patterns of activation across networks of cells, still nothing you could call red. But somewhere in all this, and we don't know exactly where or exactly how you experience red, not the wavelength, not the neural firing, the quale, the subjective experience, the redness of red, that's not in the light. It's not in your eye. It's constructed by your brain. Now you might think, fine, it's in my brain. Same difference. Not the same at all. Because if color is constructed by your brain, then brains can construct it differently. And they do. Take that 650 nanometer light again. In your eye, it triggers primarily the long wavelength cones. You see red. But wait, those long wavelength cones, they also respond to 560 nanometer light. Pretty well, actually. And the medium wavelength cones respond to 560 nanometer light too, even more strongly. So send both 650 nanometer light and 560 nanometer light into your eye together. Now both the medium and long cones are firing. Different ratio than before, different pattern. Your brain interprets this as yellow, orange, depends on the ratio. But here's the beautiful part. You can create the exact same response, the exact same firing pattern in those 2 types of cones with a single wavelength around 580 nanometers. One wavelength that looks yellow, or 2 wavelengths, 650 plus 560, that look the same yellow, physically different, perceptually identical. This is why your computer screen works. It has 3 colors of pixels, red, green, blue. When you see yellow on the screen, there's no yellow light. None. There's red light around 650 nanometers and green light around 530 nanometers hitting your eye in the right proportions to create the same cone response as actual yellow light at 580 nanometers would create. Your brain can't tell the difference. It's not seeing the wavelengths. It's interpreting the cone response ratios. Same trick with white. Look at something white. What wavelength is white? There isn't one. White is what your brain constructs when all three cone types are stimulated roughly equally. Could be all wavelengths together, actual sunlight, which contains the full spectrum. Could be just three, red, green, and blue in the right balance. Could be yellow and blue. Physically different, perceptually identical. The screen you're reading this on, three colors of light. That's it. Red, green, blue pixels, various intensities. From these three, your brain constructs millions of colors, but the physical reality is just three wavelengths at different brightnesses. The richness, the variety, the subtle differences between colors, your brain is creating all of that from three numbers, the response levels of three types of cells. Now it gets stranger. Some people have 4 types of cones instead of 3. Actually, about 12% of women have a genetic variation that gives them a 4th opsin type, usually with peak sensitivity between the medium and long wavelengths. They're called tetrachromats. For them, combinations of wavelengths that look identical to you look different. They can distinguish colors you cannot distinguish. They see color distinctions that don't exist for you. Are they seeing more colors? That's not quite right. They're having different experiences in response to the same physical light. The light hasn't changed, the wavelengths are the same, but their brains construct different perceptions because they have different sensors. Going the other direction, some people have only 2 types of cones, dichromats. Most can't distinguish red from green. Both look the same, usually yellowish or brownish depending on brightness. Not because they're seeing red and green and confusing them, they literally have the same experience looking at both. The same wavelengths that cause you to have 2 different experiences cause them to have one experience. The light is identical in both cases. The difference is entirely in the construction. Even among people with normal 3-cone vision, there's variation. The opsins aren't identical. Small genetic differences shift the peak sensitivities by a few nanometers. Your red cone might peak at 559 nanometers, while mine peaks at 556 nanometers. This means we have slightly different responses to the same wavelength combinations. We might both call something orange, but the actual experience, the quale, might be different. And we'd never know, because we can't compare experiences. You can't describe red to me except by pointing to red things. If my internal experience of 650 nanometer light is what you would call blue, if you could somehow feel it, but I've learned to call it red because that's what everyone calls things that reflect 650 nanometer light, we'd never discover the difference. We'd both point to the same objects and say red. We'd both stop at red lights and pick red apples, but the experience might be completely different. This isn't philosophy. This is physics running into neuroscience, running into the limits of what we can measure. We can measure wavelengths precisely. We can measure cone responses. We can measure neural firing patterns. We cannot measure experiences. And we certainly can't compare them across brains. But it gets even stranger when you realize what this means about reality. Color, as you experience it, is a property your brain assigns to objects based on the wavelengths of light they reflect. But an object doesn't have a color. It has a reflectance spectrum, a graph showing what percentage of each wavelength it reflects. This spectrum is real, physical, measurable. But here's the problem. Many different spectra can create the same color experience. This is called metamerism. 2 objects can have completely different reflectance spectra. One might reflect mostly 580 nanometer light. Another might reflect the combination of 650 and 530 nanometer light, but create the same cone response ratios, so your brain assigns them the same color. Under different lighting, this breaks down. Incandescent light, fluorescent light, LED light, sunlight, these all have different spectra. An object that looks the same color as another object under one light source might look completely different under another because the reflectance spectra interact differently with the different illumination spectra, creating different cone responses. You've experienced this. You've bought clothes in a store that looked the same color, brought them home, and discovered they're different. Not because the clothes changed, because the light changed. The reflectance spectra were different all along, but you couldn't tell because under the store's fluorescent lights, they created the same cone responses. The color you see depends not just on the object, but on the light source and on your particular cone sensitivities. Change any of those three, and the color changes. The color isn't a property of the object. It's a property of the interaction between object, light, and observer. Now you might say, fine, but the wavelength is real. That's what color really is, the wavelength. Wrong. Go back to the computer screen. Yellow on the screen. Red and green pixels. No 580 nanometer light. Yellow lemon under sunlight. Actual 580 nanometer light. Same color experience. Different physical situations. If color is wavelength, these should look different. They don't. Or consider this. Mix red and green light. You see yellow. Mix all the wavelengths of the rainbow together. You see white. But subtract just the green wavelengths from white light, leave everything else, and you see magenta. Magenta. Look at magenta. What's its wavelength? There isn't one. Magenta doesn't appear in the rainbow. It's not in the spectrum of visible light. It doesn't have a wavelength. It exists only as a brain construction created when the long wavelength cones and short wavelength cones are both stimulated, but the medium wavelength cones aren't. This particular pattern doesn't correspond to any single wavelength. Your brain invents a color for it. Magenta is your brain's solution to a problem. The problem. The short and long cones are firing, but the medium ones aren't. This doesn't match any wavelength I know about. What should I show? The solution? Magenta. A color created entirely by your brain to fill a gap in its model. This reveals what's actually happening. Your brain has a color space, a model of possible color experiences. This space has 3 dimensions because you have 3 types of cones. Every possible combination of cone responses maps to a point in this space, and your brain assigns each point a color experience. Most points correspond to specific wavelengths or combinations of wavelengths, but some points, like magenta, don't correspond to anything in the physical spectrum. Your brain creates colors for those points anyway. The color space is a construct. The colors are constructs. Labels your brain applies to patterns of neural activity. Let me be clear about what I'm saying. The electromagnetic radiation is real. The wavelengths are real, measurable, physical. The reflectance spectra of objects are real. The absorption spectra of cone opsons are real. The neural firing patterns are real. All of that is physics, chemistry, biology, completely objective, measurable, the same for anyone who measures it. But the experience of color? That's not in any of those things. That's something else. Something that emerges from neural processing in a way we don't fully understand. And that experience can be different for different observers, even when all the physical measurements are identical. This is not to say color is an illusion. The experience is completely real. You really do see red. But red is not a property of the light or the object. It's a property of your experience. A quale, a mental event. And we have no idea how to explain it. We can trace the entire chain: photon absorption, molecular conformational change, ion channel dynamics, action potentials, synaptic transmission, cortical processing. Every step is physics and chemistry. Nothing there is mysterious. But at the end of this chain, you have an experience, the redness of red. And we cannot explain how physical processes produce that. This is the hard problem of consciousness, not just for color, but for all sensory experience. How does electrochemical activity in neurons become subjective experience? We don't know. We have the neural correlates patterns of activity that correspond to experiences. But correlation is not explanation. You might think I'm about to tell you the answer. I'm not. We don't have one. This is where physics ends, and neuroscience hasn't caught up yet. Maybe it never will. Maybe subjective experience is fundamental, like charge or mass, something that exists, that we can measure correlates of, but can't reduce to anything simpler. But here's what we do know. Color is not in the world. It's in you. The world has electromagnetic radiation at various wavelengths. You have sensors that respond to narrow bands of those wavelengths. Your brain interprets the sensor responses and constructs an experience. That construction is so automatic, so immediate, so compelling that it feels like you're perceiving something out there. But you're not. You're experiencing your brain's model of something out there, a model built from 3 numbers, the firing rates of 3 types of cells. Everything you see is like this, not just color, brightness, shape, motion, depth, all constructed by your brain from patterns of neural activity. You never directly perceive the world. You perceive your brain's model of the world, built from fragmentary sensory data. The world doesn't look like anything. Looking is something your brain does. The experience of seeing, of color, of vision, that's in your head, not out there. This doesn't make the world less real. The electromagnetic radiation is real. The objects are real. But color, the way you experience it, is additional, a feature your brain adds to its model to help you navigate, to help you distinguish ripe fruit from unripe, to help you find a mate with healthy skin tone, to help you survive. Evolution didn't design your visual system to show you reality as it is. Evolution designed it to show you a useful representation of reality. Color is part of that representation. Incredibly useful. Completely constructed. And once you realize this, once you truly understand that the red you see exists in your brain, not in the light, not in the object, you can't unsee it, you look at a red apple and you know that redness is you. Your brain is creating it right now, in real time, as photons hit your retinas and neurons fire in patterns, and somewhere in the tangle of 100 billion cells, redness appears. The world is colorless, electromagnetic radiation at different frequencies. You are the color. All of it, every color you've ever seen, you created.